Hi everyone, thanks again. I hope you enjoyed tea. There is dessert afterwards, so a lot of it. So I'm actually not too sure what it was. What was it, Jim? Apple crumble. Hope you folks in the room. So this sort of virtually wraps up the event. Tomorrow's nature walk has been postponed because of the wet tracks out there, so they said that it will be shut. So MPAS, we're going to be trying to be out of the camp, locked up by 10 o'clock, so we can head down to Cool Art. So those that want to go to Cool Art and have a visit and don't know where it is, come and see me after the talk here, and I'll try and describe to you where it is without getting you too lost.
Into Cool Art Road.
Into Cool Art Road. When you talk Cool Art, everyone's got GPS in there, don't they?
Yeah.
Right. Cool Art Road. You'll find it.
Yes.
I'll stand there, sit down. Brad, you can take over the talk. Thank you for coming out tonight in this wet, cold. And there's the last two stragglers, so I'll get out of the way.
That's right. No, yeah. Thanks for having me. This isn't cold. It's not Canberra, right? Canberra's either cold or freezing over because all the politicians are there. So either way, we lose. Thanks for having me. Today I was going to talk about a variety of things that I'm doing, that kind of Australia is doing. It's as everyone obviously knows that we're just past 50 years since the moon landing, and I think it's kind of nice because there are a lot of things happening, and they're happening at a faster and faster rate, which makes it, I think, quite exciting and fun. And so there's kind of this area where now anything and everything's possible, and that's what we get to do, and that's what I get to do, and talk about it, because it's fun. So I guess just firstly, though, I'd like to start by acknowledging and celebrating the first Australians on the traditional lands we meet, and pay my respects to their elders, past, present, and emerging. Because it's important, right? We always talk about the future and what's going on now, but everything we know is related to the past, right? The present is a very irrelevant thing because the present doesn't exist because it's already in the past, right? And so we have to remember that. So let me start with this. All right, who's heard of Stonehenge? This isn't. It's you all passed. Good job. You all have dessert. Who's heard of Wurdi Youank?
Yeah.
Good. I expect this state to have a number of people who've heard this. So those who don't know, you do not get apple crumble. Well, actually, I think you do, given how much they made. So, all right, the other people get double served. And so it is this rock formation on the other side of the bay. And some astronomers a while ago mapped the position of it. And it traces the solstices and the equinoxes perfectly. In fact, I guess what sometimes you don't realize, it traces the movement of the sun better than Stonehenge, right? So it is more accurate than Stonehenge. And it's also 5,000 years older than Stonehenge, right? It's 11,000 years old. It is the oldest astronomical experiment in the world, right? And it's not too far from here. And I think this is important when we think about what Australia is doing, because it is a lot, and it doesn't just start now. We heard all the great stories of how Australia played this critical role with NASA, and I think sometimes it was forgotten that there were hundreds of people employed by the U.S. government, employed by Apollo, essentially the Apollo missions to put two humans on the moon. And so it is this nice way of showing what Australia is and will do. This plays, yeah. So I have a question for you, for those who don't get seasick watching this. Is this taken in space or not?
No.
No?
Yes, it is in space, but I think it's on a balloon.
Okay, so all right, so it is on a balloon. If you think yes, raise your hand. There's a few. If you think no, raise your hand. So the no's are correct.
There must be an atmosphere on the balloon.
Well, the Earth's atmosphere extends for 2,000 kilometers. Right? So this was taken at 42 kilometers. Does anyone know where space starts?
100?
100, yes. Does anyone know the actual reason why it starts at 100? Because it's a round number. Yes, you're all correct. And this is the funny thing. Not only are astronomers lazy and suck at math, but no, it's actually not even a science reason. It's a legal reason. And this is actually important when we think of space and space exploration. A lot of the issues we're facing now are not technically or engineering or science issues. They are these other issues. And so this issue of space law, which is a big deal, and there are space lawyers, there's 6 of them in Australia. In fact, 2 are married, so like a third of Australian space lawyers live in the same house. But it's one of these things where it's becoming a bigger and bigger issue. Here, I'll explain why. Okay, so you're going to be Australia, all right? Now you're a satellite company in Australia, okay? Now you're New Zealand. Don't look so sad. And you're a rocket company in New Zealand, all right? So the Australian-built satellite is going on the New Zealand-built rocket. With me so far? This happens like once a month, all right? But the Australian-built satellite on the New Zealand-built rocket isn't going to launch from Australia or New Zealand. You're going to launch from French Guinea. You're French Guinea. And Europe launches all their satellites from French Guinea. Again, not an abstract thing. With me so far?
Yeah.
So the Australian-built satellite and the New Zealand-built rocket is launched from French Guinea. But that satellite crashes into the Russian satellite near Russia. Who's legally at fault?
She is.
He is?
Sorry, she is.
She is?
Yes.
French Guinea?
Yes.
All right. Any other ideas? All of them? Russian? That's the American answer. So it is French Guinea.
Yeah.
The current law is they who touched it last.
Yeah.
So it is a bit childish, but the law was built around treaties in 1967 while only countries from their own land launch their own satellites. Right? Right? You know SpaceX? Right? You know how they land on barges? 20 kilometers offshore?
Yes, yeah.
International waters.
Yeah.
It's a legal choice.
Yeah.
They can just as easily, technically, if they need to, land on land, and they do. But they also land on barges because then they're not legally held accountable if something goes wrong. So everywhere you start to see, there's these legal choices. A good example of this is, all right, so Russia, we'll pick up Russia again. You know those like the Russian nesting dolls? Russia built the satellite version of that. So they launched a satellite, and then out of that big satellite, a smaller one popped out. And then a smaller one popped out of that one in orbit. Now, besides being very cool and very stereotypical, the second and third satellites, no one launched. No one's legally at fault for whatever they do. And so everywhere you start to see in the world of space, there's all these little legal things that are becoming a bigger, bigger issue. So yes, this was taken from a balloon that just popped. In fact, so this video wasn't from this one, but one of the things I actually do now is we launch a lot of these balloons. So these are what we call these high-altitude super-pressure balloons. They're about 2 stories tall from top to bottom. And we have large telescopes that we've built and mounted to the bottom of them. And the reason you do that is because, well, let's start here, go back. You're almost in space, right? The balloon goes up. These balloons can stay in the air for 6 months at a time, and they're actually fairly stationary. But then, instead of like a satellite, the balloon just comes back down and lands, and then we refill them and we relaunch them. We actually have about 16 in orbit right now over Australia. So this is from flight radar. So where you're tracking airplanes, you can go see our balloon icons. And so one of the goals is that we're actually aiming to build 50 of these in this ring to do especially what we call an ultraviolet survey. So ultraviolet light is absorbed by the ozone, right? So if it gets through, we get burnt. But ultraviolet light tells us a lot of things. It tells us a lot of special things that is actually quite interesting. One of the things that we're doing with them are finding these. So my specialty is supernova. And supernova are great. They're just giant bombs. And they happen all the time. every second, there's 50 of these that go off, right? So when you're having lunch in the course of an hour, 180,000 stars explode. There's a lot of them. I call it employment, but it means that there's a lot of things to find. And they're very energetic, and they tell us a lot about the universe. And the reason we're trying to spot them now with ultraviolet colors is they do very few special things. So firstly, the majority of these ones, or if you don't know, are what we call core collapse stars. So these are a big star, and in the inside of this star, the core starts to collapse. So it's kind of like, imagine you take a scoop of dirt or sand, and you squeeze it, and you keep squeezing, and you keep squeezing, and you keep squeezing. The moment you can't squeeze it anymore is the moment a black hole or a neutron star is created. Once you create that black hole, your hand rebounds, and it goes through, and it produces a shock wave. And this shock wave ignites and explodes the star. So imagine a nuclear bomb, right? You get the flash, you get the shock wave, and then you get the nastiness behind it. That's literally what a star does when it explodes. In fact, one of the things that I've done in the past few years, we've actually seen this shock wave within minutes actually igniting stars. We've done it with Kepler. So for those who don't know Kepler, it was a telescope that was famous for finding all these planets around other stars. But what we did was, firstly, Kepler broke. So you have to point in 3 dimensions in space, and so you have these reaction wheels that are essentially gyroscopes that help you build or point. NASA being NASA built 4 of them in there, so they had a spare. NASA being NASA, 2 of them broke. So you can only point in 2 directions in 3-dimensional space, which is completely pointless. However, the cool thing is we figured out that if you use light from the sun, the actual light particles, what we call photons, they bounce off the side of this telescope and pushed it like a sail through space. So, do you ever hear that light moves as a wave and a particle? We know that because we fixed a broken spacecraft with that. And it worked. And now, one of the cool things it did allow us to do was to detect these shock waves. So this is kind of an animation. But so this is in minutes. And so inside the star right now, it's collapsing inside. And it's getting smaller and smaller and smaller. And then we reach the point and can't collapse anymore. The shock wave goes through, ignites the star, and it explodes. So we saw that shock wave to within minutes. We saw the moment an actual star was ignited and exploded. And there does a cool thing. So you might have heard, was it Carl Sagan, you're all made of star stuff? What he didn't say is you're all made of dead star stuff, right? It's not as romantic, but it's actually more accurate. And that's because when this star ignites, it blows up the star, and all of the atoms, all of the stuff that makes up the star is broken apart. And then over time, it cools down, gravity pulls it back together, and it forms new stuff. And we know this because we detected it. In fact, if you look here, so this is kind of brightness versus time. So these are every time we measured every 30 minutes. So it got brighter, 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 brighter. It reached its peak brightness. Then it started to decrease, it started to cool and fade. Then we got this other bump. This is the exact moment hydrogen formed after that star exploded. And then it cooled down. That's the exact moment helium formed. And we think that's the exact moment lithium formed. You can literally see the creations now of the elements of the universe in real time. And this is what happens when stars explode. They produce us, they produce everything. Now, there is another type of star which will be more relevant a little bit at the end, and that is what we call the thermonuclear one. And that is if you take a white dwarf, so kind of something our sun will be in 5 billion years, and it's near another star. Well, the gravity of that white dwarf can suck off the atmosphere of the star. And we use these because they're useful for measuring distances across the universe and how fast the universe is growing. Because of essentially a very simple equation. Does anyone know what it is? Think Einstein. E equals mc squared, right? Energy equals mass times the speed of light squared. Well, firstly, what goes at the speed of light? Light. And so when you convert mass to energy, you get energy. Now, if you have the same amount of mass always exploding, you produce what? Same amount of energy. And so we can measure the energy or brightness over distances and see how it changes. And so this type of star happens to blow up at the exact same mass, what we call the Chandrasekhar limit, 1.44 times the mass of our sun. And so by doing so, we can actually see and use how the universe is growing. But it's all dependent on knowing exactly the mass of this. Well, how do we do that? We see the shock wave rip apart the star. What we're now able to see is we're actually able to see what we call the Roche lobe, or the suction of this white dwarf. And we're able to see the exact moment it reaches 1.44 masses, it explodes and produces the shock wave. Because that shock wave hits the other star, strips it, and flings it out into the solar system or the universe. And we can see this in real time. We can actually think we can detect two white dwarfs colliding. They produce other things like gravitational waves, but we can actually see the shock wave that is produced from these two things colliding. And we've done all of this with Kepler. But all of this is bigger and brighter and more energetic than the ultraviolet, right? So if you want to find more of them, or if you want to understand how different stars evolve, or how much energy there is, you need to look at the ultraviolet. And something else that produces a lot of ultraviolet light are black holes. And not necessarily the black holes themselves, but you notice that there's kind of this ring of star around these black holes as they merge. Well, as those rings collide, stuff collides. And it bursts. It bursts light. So it mostly bursts X-rays, but it also bursts a lot of ultraviolet light. So by mounting these telescopes on the top of the balloons, we can actually predict the moment black holes collide before they produce ripples in space we call gravitational waves. And so this is what we're doing now with these giant telescopes on these balloons. So it's kind of something really cool that is literally above our heads. Well, not our heads, most of Central Australia, that we're able to do and see. And it's kind of it's a nice thing that things are evolving. Now, I just want to step back real quick. We kind of jumped to falling into black holes, but there is a lot happening even with respect to the moon. Often people always wonder why we haven't gone back in 50 years. And I think it's two reasons. You have to realize that going to the moon in the first place, the whole point was to get to the moon, right? So when people got to the moon, it's kind of, well, what now? It also costs $180 billion to get to the moon. And that's a lot of money. But now there is a new goal, and that is obviously to get to Mars. But the way through to Mars is through the moon. And this is kind of the coolest project, I think, that is not necessarily appreciated. It's called the Gateway. This is a space station that will be built around the moon. The first two modules here and here are being designed. And so the idea here is that astronauts up to 4 can spend about 1 to 3 months at a time in orbit around the moon. They can go down the surface for experiments. They can do experiments in orbit. And more importantly, stuff can dock with the space station, refuel, and then take off to go towards, say, Mars. And this is being built, in fact, the first mission of the Orion capsule, the new, essentially the new replacement space shuttle, the new reusable U.S. space vehicle, is set to take it up. And Australia will be a partner in assembling this soon, and developing it. And it's kind of cool to think that in a few years' time, there will be a space station around the moon. Like, that is something I think we never would have imagined happening, but it is. And the reason this interest is in the moon is because there's stuff we can use. The moon has lots of water, it has lots of ice. Now the great thing is, ice happens to be hydrogen and oxygen, right? Well, the most common source of rocket fuel is hydrogen, which is hydrogen and oxygen. You just turn ice into rocket fuel. It's not rocket science. It's this kind of cool, simple idea that works. Now, obviously, the trick here is you have to mine or extract the ice or the water on the moon, and that is something that we are working on. And the whole goal, obviously, is to get to Mars. Now, Elon Musk wants to get to Mars, great for him. I really don't want to go to Mars. You don't have brain, but one of the things I don't think we appreciate is how dangerous it is to get to Mars. And there's a lot of work that needs to get done before the first humans, I think, even get there. So I guess I'll say, actually, all right, I'll ask you a question. Who thinks that there will be a human on Mars alive for at least 1 minute? All of those qualifiers are important.
Anytime in the next 100 years?
Anytime.
Yeah.
So, no time limit. So at some point there will be a human on Mars alive for at least a minute. If you think yes, raise your hand. That's fine. Now, who thinks that aliens exist? Now, when I say aliens, we mean, in the truest sense, life not from Earth, right? Now, it can be bacteria, plants, animals, things in camera. Now, here's the real question. What do you think is going to happen first? That we find evidence directly that aliens exist, life exists somewhere else, or there's a human alive on Mars for at least 1 minute? If you think alien first, raise your hand. If you think Mars first, raise your hand. Okay. So I'll give you my answers. I mostly think there will be a human alive at least for 1 minute. Because you can't survive for 5 minutes without anything on Mars before you die a horrible, what Matt Damon should have gotten death. But you have to get there. I definitely think life exists. I even think intelligent life exists, assuming we're intelligent. Or something like us would be intelligent. But I by far think we'll find life before we have a human on Mars. I think there's a solid chance that we'll detect life on Mars by 2022. And I think not only is it just because of how close I think we're getting to finding life somewhere else in the universe, but how hard it is to get humans to Mars. I mean, when we look at Mars, it looks a lot like Australia, right? It's dry, it's desert-like, but you can see evidence of water flows on Mars. We know the surface of Mars was rich in water. And one of the interesting things about Mars in recent times, it is well concluded that we think there are these subterranean oceans of liquid water, salty water, kind of like brine, on Mars. And so if you dig deep enough, you will hit water. Now that water can obviously be used for drinking, it could be used for rocket fuel, but it could be to look for life. Now, one of the things that is reliant on humans on Mars is, again, our ability to extract, i.e. mine, stuff. And that is something we are working on. There's this mission called Hayabusa II. And so this is a JAXA, Japanese Space Agency-led mission, that Australia is a partner in. And so late last year, it arrived at the asteroid Ryugu, and then it started to deploy these little canisters on the surface. And so this is a photo from the surface of the asteroid. And a number of weeks ago, I think it was in February, March was the first one, and there was another one about a month ago. The probe went down to the surface, so this is a real video on board the probe. And the probe will go down to the surface, and it will do a touch and go maneuver. So essentially, it will suction up or extract as much rock and mineral as it can and pop back off the surface. So it'll reach the surface in about 5 seconds. So here we go, we've touched down. There's all the rock, there's the probe descending off. So it sucks up as much of this rock, essentially as much of this metal as it can. It did a second maneuver, as I said, a few weeks ago. It will do a third one, a third maneuver. And also in the meantime, it actually did a maneuver where it deployed a canister that contained 10 kilograms of C4 and blew a hole in the asteroid and extracted that as well. The entire probe, or at least this capsule, will come back and land in Woomera in South Australia in November 2020. So, we can already do it. We're already working on it. And so this whole idea that we have to start extracting things in space is actually something that is here and now. In fact, if humans are going to have a future going to Mars, going to other places, it is that we're going to have to perfect our techniques of mining. And this is something that Australia is really working on already, and it's where the future is headed. And it's something that Australia can really use, obviously, its expertise in mining to do, but there's a lot of other tangible benefits that you can have, right? These asteroids are just giant chunks of metal. You can get 100 years worth of nickel and lithium from one asteroid. And it's actually not that hard. We're already working on it. And this is kind of now where the future is headed, is that we can start extracting things in space. We can start building things in space. In fact, NASA awarded a number of contracts 2 Fridays ago now to private companies. One was essentially to 3D print things in space, right? If you can extract things in space and you can make it in space, you don't need to bring things up into space. Because right now it's expensive. Just to get something into low Earth orbit, just about 400 kilometers above the surface, it's about $20,000 a kilogram. So if you think about it, right? So let's say you're a human. Sorry, you are all humans, right? You're a human, you need to drink water. So let's say you need to drink 8 liters of water a day. So that's 8 kilograms, so that's $160,000 in water per day. So you need to be up in space for 3 months. You're talking about 90 days, so you're at $4.5 million just in the cost of water. It's expensive. And that's low Earth orbit. We're not talking about the moon, which is much more expensive. We're not talking about Mars, which is absurdly expensive. And so when we think of old Matt Damon, it is really hard to try and do this without being able to extract things from the surface. And this is the only way it's going to have to be done, is we can't be reliant on just sending stuff there. We're going to have to start doing it independently in space. And that is the future of space, is doing these things. I think one of the things, though, when we talk about sending humans everywhere, the hard part isn't really the technology. The hard part is really the human. When we think of space, we think of no gravity. I mean, there is microgravity, but we think of no gravity. We think of no atmosphere. I mean, the Earth's atmosphere does extend for a while. Mars does have an atmosphere that's mostly carbon dioxide. The moon has the thinnest of atmospheres, nothing you could really use. You think of space as being cold as well, right? Space is cold. Yes. Is it?
Yeah. Well, I think it is.
And hot. Right? Space is cold and hot. This is important. That astronaut, so this is a real photo. This is Bruce, what's his last name? So he was the first astronaut to do an untethered EVA, an untethered spacewalk. NASA built a jetpack and stuck him in it and floated around. When you go around the Earth every 90 minutes, for 45 minutes, you're away from the sun, and it's about minus 150 to minus 170 degrees Celsius. 45 minutes later, you're in front of the sun, it's 150 to 170 degrees Celsius. The human body doesn't like going from minus 150 to 150 every 90 minutes. Right? The reason these things are so big is that they have to have their life support. They have to have their oxygen. These are 100% oxygen environment. If you have an electrical spark, your astronaut goes kaboom in space. This is just how the risk they have. One of the problems that is realized is that these astronauts go through a lot of health issues. Astronauts have a huge amount of health problems that aren't necessarily well publicized. A good example is the spacesuit. So the spacesuit weighs about 180 to 200 kilograms, depending on what they're carrying. Right? Now in space, this doesn't really matter because there's no gravity, so you don't feel 200 kilograms. But what happens when you come right back down to Earth? It weighs 200 kilograms. Astronauts have a huge rate of shoulder reconstruction surgeries. They tear their shoulders. And something like 40% of all astronauts have both shoulders reconstructed because it just tears their shoulder. Astronauts have weird cardiovascular problems. In fact, space messes with astronauts' eyes. Most astronauts are not even allowed to drive when they come back because they can't see properly. There's an ultrasound machine on the space station that can detect how your eyeball changes in space. Right? And it's a classic example of this. When there's no gravity, fluids move differently in the body. So one of the well-known syndromes is puffy head, chicken leg syndrome. That your head becomes puffy because blood goes to it, and you get less blood in your legs. Do you know why astronauts exercise? Yeah.
So because their bones lose calcium and they need to get active.
So their bones lose calcium, but why are they worried about that?
Because they can just snap when they go back down to Earth.
So, kind of.
Calcium's a neurotransmitter as well, and also cardiac conductive.
So there's cardiac. One of the big issues is they worry about kidney stones, or all that calcium goes into your blood goes somewhere else.
Yeah.
There have been astronauts early days that had kidney stones in space. Yeah, exactly. Right? Astronauts have so many health problems. They can't necessarily sleep well. They can't necessarily eat well. They can't even stand up when they come back down. So they do worry about their bones breaking. They also don't have enough oxygenated blood going to their brains. Every time they stand up, they faint. So astronauts are kind of beaten up in space. And one of the, so actually I'll ask this. A few people might have heard this question elsewhere when I've asked it. If you know the answer right away, don't. What animal has been the most in space? Yeah?
A dog?
Nope. Good question, no. The Russians love sending dogs up, but no. Spider? No. Spider.
Chicken.
Tardigrade? No. Chicken.
Cockroach.
Monkey.
Nice.
Mice.
An ant?
An ant.
Good guess, no.
Cockroach.
Cockroach? No.
There you go.
It's not a land animal.
Oh.
A fish.
It's a type, you're getting closer.
Right.
Well,
Worm? No.
A tadpole.
A tadpole? Very close.
Frog.
Frog. Jellyfish.
Oh.
NASA's bred 60,000 jellyfish in space. Now, obviously, you're asking why. They weren't floating around. I always like it when I ask kids this, and they say, like, sharks or whales. I'm like, well, space isn't that big. No. So, when jellyfish reproduce, they reproduce quickly. They also reproduce a lot. The third reason they were chosen is when jellyfish form, crystals form in the base of their bodies. And this helps them swim. It's essentially buoyancy. So NASA bred these generations and generations and generations of jellyfish. And then they brought the last generation back down to Earth. And they couldn't swim because they formed differently in space. In fact, there's a real theory that says if there are humans who go to Mars and humans who are born on Mars, because Mars has a sixth the pressure and third the gravity, they would be crushed when they came back to Earth. They would not be able to, they would be formed differently. And this is one of the issues that we have, right? I mean, there's simple things like radiation. Now, this is kind of what the scale of radiation is. Here's how much you get when you get your X-ray. This is how much a worker should get every 5 years. So this is kind of your limit if you're to be exposed in 5 years, but you get it in 6 months on the space station. So keep in mind, this is 6 months just going around the Earth. This is the career limit of a U.S. government employee, NASA. This is how much you get going to Mars. U.S. government employees through workplace health safety laws cannot go to Mars. We don't. Now, radiation you can potentially solve, but there's other things that pop up. So in 2015, NASA and Russia each put an astronaut on the space station for a year. Now, Scott was chosen because he's an identical twin. And this is important, so both twins have been into space, both twins have had various health issues. So the question was, does the twin who's been in space for a year continuously, Scott, have different health problems to his identical twin? And the answer is yes. He had longer and different health problems. And in fact, there's something called, there's coatings around your chromosomes, telomeres. And it's kind of a measure of age. And the telomeres around Scott's were different than his identical twin. The identical twins at a genetic level were not identical. Because one was in space for a year. Now, we're talking about very minute things, but these are just a year around the Earth. The quickest we can make a trip to Mars, staying there and coming back, is 940 days. That is kind of the quickest it's going to happen. That's a long time. And so when we start to see these things, these are only done on the scale of 3 to 6 months near the Earth. We're still relatively protected. Going through space to Mars, going to Mars, is a completely different ballgame. I mean, there's even the simple fact that you have to be stuck in a thing for 900 days, right? So there's been these psychological experiments where they willingly get these volunteers to lock in these bubbles for 3, 4, 500 days, right? So, imagine being locked in a room for a day with a few people, and then imagine 500 of those days, and there's nothing to do. Welcome to Mars, right? I mean, it is a big deal. And so a lot of these experiments have been, I don't hear this. I'm loud, but that's right. A lot of these experiments they've been doing now have been trying to lock in people in these bubbles to see what is the psychological impacts. In Europe, they put them in caves. No sunlight, it's remote, they have to work together, they stick them underwater. They put them in the most inhospitable places you can imagine because you want to see what is it like to work. Because on the space station, they have an emergency capsule. If something goes wrong on the space station, they can evacuate and come back down to Earth. You can't do that on Mars, right? On the space station, you have a schedule, and you keep that schedule. You call home, you have a sleep, you have eating. On Mars, you don't have that, right? You can't even call home because the delay of sending a signal one way is 25 minutes, right? 25 minutes to Earth, and then Earth has to reply. So it's a 50-minute delay just to talk to your family. I mean, we have the Indians, so we understand these issues, but other countries don't. And so this is one of the problems. How do you even kind of deal with being on a different world? And this is kind of the struggle that people are finding is we don't know how well humans are going to deal with going to Mars. Physically, mentally, socially. And this is kind of an interesting thing, but yet this is the thing that Australia is starting to build. One of the very first psychological experiments was designed by an Australian in Canberra. I know about all the health stuff because my wife has worked on this mission. And so we're starting to use our expertise in other sectors beyond, say, normal technology or engineering to really advance or try and think about how humans are going to survive their trips into space and how humans will get to the moon, back to the moon, and how humans will get to Mars. Now, we can take out the human, and we do. And so this is a view of Earth with all the satellites around it. Currently about 4,500 satellites in orbit, and half those are just spying on other satellites. One of the problems we're really starting to have now is space junk. As these satellites go up and up, some of them become defunct. And in fact, in 2009, we saw the first crash between two satellites. So in this case, it was Russia's fault. So this Russian satellite, they lost communication and control with it, and it crashed into this Iridium satellite phone. And so 90 seconds later after impact, 8,000, almost 10,000 pieces of debris were created. And so that's just stuck, orbiting around the Earth. Now, we worry about things colliding, right? All the gravity, which, even though the movie had no gravity in it, it should have been called Angular Momentum. At least George Clooney turned into space junk, so it was fine. Now, we don't, look, obviously this is very Hollywood, but there have been, I think it's 11 times that astronauts have actually had to get into the emergency pod of the space station because it's about to be hit. It is not an abstract issue. In fact, this is a photo from Bulletproof Glass from one of the space shuttles. So the space shuttle, essentially the glass was bulletproof. And this hole is 5 centimeters deep, and it was caused by a piece of paint. Right? You're traveling 40,000 kilometers an hour in space. Think of a bullet traveling 700 kilometers. Make that bullet go 40,000 kilometers, you get that. And so one of the things that we're starting to embark on at Mount Stromlo and across Australia is that we're building laser systems. So these lasers, they find an object a centimeter wide, 3,000 kilometers above the Earth. But then the idea, and the laser should come online next month actually, is that we can actually use the lasers to start deorbiting the debris. So we can literally use the laser. So you can imagine, so this stuff's like water spiraling down the drain. It is slowly going back to Earth. Just takes 20, 30, 40, 50, sometimes 100 years. And we use the laser to shoot it at it. And so that pushes it straight up. So then gravity pulls it straight back down and then burns up the atmosphere and we get rid of it. So we can actually start deorbiting stuff now in space. And so, you know, these are big parts of the problem of humans in the future going into space. If we're going to do it safely, we kind of need to clean up space and we need to do it pretty well. Now, I just want to touch on something to finish here. You know, we talked a bit about stuff near the Earth, we talked about stuff blowing up. And we do know a lot about our universe, about 93 billion light years across. And one of the problems, though, is we're trying to figure out or see the very beginning. Not the cosmic microwave background where we see this kind of the relic light after the Big Bang, but we want to see the first stars, we want to see the first galaxies, we want to start imaging these planets that we're finding, right? We're finding thousands and thousands of planets. Every week we find new planets. We want to start looking at these planets. It's not just, can they host life? Do they have an atmosphere? Do they host life? We want to start doing that. And one of the things I'm involved with and a bunch of us are doing, and Australia's a partner of this, is this. It's called the Giant Magellan Telescope. So this is a new telescope being built in Chile, and so it'll be 25 meters across. So it'll be 25 meters side to side, so you can see a person to scale. So this will be one of the largest telescopes, well, it will be the largest telescope built on the ground. It's not being built in Australia, because we have rain. It's being built in Chile, where most people know there is no rain, and people panic when it rains once every decade. And it's also going to be giant, right? So here's a person to scale. Here's the Hubble Space Telescope, which is 2.4 meters. Here's the new space telescope, James Webb, which hopefully is launched in 2021 at 6.5 meters. And this is what we're building. So, giant. But you might say we're building on the ground, so our image won't be as good as, say, Hubble in space. Which in theory is true, but we found a way around it. So, one of the things that happens is, as you know, stars twinkle. So we're going to create artificial stars. So we are mounting lasers around the telescope, so the laser goes straight into the sky. So then turbulence will cause that laser to twinkle and move around. But we know exactly what the laser should look like. So we will have a computer on top that will actually change the shape of the mirror every millisecond. So if the atmosphere is wobbling around, the mirror will wobble with it. So we can just take out the effects of the atmosphere now. So if you want to put this to scale, so this is what a normal telescope that we used to have would see. This is what Hubble would see of the same area. This is the new space telescope, and this is us. So we're going from this to that. So not only will we be able to see further and fainter light, because we're 25 meters across, so we'll have 100 times the collecting area of Hubble, and we'll also have 10 times better image resolution than the Hubble Space Telescope by doing this. And also $3 billion less. And so it's a very big thing, right? If we want to start seeing past this, right? Past the deep fields of Hubble. We want to really start seeing the very first galaxies, the very first stars. We need a telescope that can do that, and that's what we're building. And it's so, it's kind of amazing what is happening in Australia right now. I don't think necessarily that we appreciate that in all these projects and all these things going on, Australia still keeps playing a critical role, just as it did 50 years ago. And it's going to keep doing that, and it's going to keep doing more and more. We have the benefit that technology is quicker, it's cheaper, we can do things faster, and it's going to keep happening in the future. And I think it's kind of a great time to be doing astronomy in space in Australia. And it's going to keep being a great time to be doing astronomy in space in Australia. So I think I'll end there. Thanks. What did you to.
There's a question?
Yeah, questions? Yeah. Sure.
Funding for this amazing thing that Australia's doing that I didn't know about.
This.
Is it government funding? Is it private funding?
Okay, so Australia has a 10% share in this telescope. It's done with U.S. partners as well.
Yep.
The share is half paid by ANU and Mount Stromlo Observatory, and the other half was paid by the Australian government. So in fact, half of it was paid from RUD money during the GFC that we became a partner. The other half was from ANU that we actually used from insurance money from the 2003 bushfires in Mount Stromlo.
Oh, okay. Good.
Yeah.
I'm just so thankful that you've been reinforcing what I've been speaking to my students about for Mars.
Yes.
Over
Don't go.
We had, we had the close approach, and of course
Yes.
Mars was a big thing, and it was sort of a main subject of mine over with students. And I think that really reinforces what you said is there's so much hype about going to Mars, and 2050 we'll have a man on Mars, anything like this. It's just, and someone was talking about what you were talking about, the industrial side of it. All our mining can be done on the moon, but who are the people who are going to go there to do it? Who are the people who are going to sacrifice their lives, basically? Because that's what they'd be doing. What comes first? It is a conundrum. And the other question I had, before the deep space photograph was taken, astronomers thought we'd be looking back in time then and they'd see young galaxies which hadn't completely formed. Do you think it's possible that this could happen with this one, that we look back in time and see galaxies that are perfectly formed?
Yeah, so I think just quickly on the Mars real quick, though, I think there's always going to be risk with anything we do in space. I mean, there's technically risk with airplanes. I think it's all about mitigating the risk. But I just say you have to note that, as you said, 50 years ago, the goal was the moon in 9 years. Now NASA's openly admitting it's going to take 20, 30, 40 years to get to Mars because it is that much harder, right? In terms of the first galaxies, it's one of the questions is to actually see what the very first building blocks of stuff look like. Or, what were the very first stars born in the universe? That is one of the goals. There's this theory that stars 50,000 times the mass of our sun existed, and that gave birth to the second generation of stars and then galaxies and stuff like that. That is one of the things that this and the James Webb Space Telescope. So the idea here is we will look in the optical light. James Webb is being designed to look in the infrared light. We'll work together to try and hopefully find. I think with everything, we'll just keep pushing the bounds and saying there's more and more and more. And I think that's the great thing about the universe is it has no end in theory. It has no end in practicality. It has no end that we can detect. And I think we'll just keep finding that it just keeps going further and further and further away, and that mystery just deepens and deepens. So I kind of like to think about what we're going to discover that we don't know. If you think about since Hubble Space Telescope was launched 28 years ago, and all the stuff that's found, we've gotten a generation now of knowing a planet around another star, in only a generation. We've known 95% of the universe has only been discovered in the past couple decades. And so it's kind of an exciting time to think what that next generation is really going to do and how out of date our picture of the universe is in 25 years. Again, employment, which is great, but it's a true thing, and I think that's a great thing. Sorry, in the back.
Just in relation to, you talked previously about the drop-on probe.
Yeah, Hayabusa, yeah.
Is the intention to bring the rocks back to Earth?
Oh, yeah.
Right. So, what I believe with some of the shows that we're seeing with Brian Cox and so forth, when it comes to trying to detect life, like satellites like the Rolfe and so forth, stuff like that, there is a considerable effort made not to colonise or introduce bacteria into the system. And if you believe in the hypotheses of panspermia, seeding from comets and so forth, in relation to bringing back possible bacteria from the rocks that has been empirically proved that can exist and survive impact, temperature, ignite, is there a certain risk in relation to bringing back these rocks back to Earth?
Oh, definitely. And you should feel confident we don't know how to solve it. So, no, I mean, yes, completely. I mean, just on that, right? Israel just announced 4 days ago that on their probe that tried to land on the moon, that didn't land on the moon, they were carrying tardigrades, these extremophiles. And so they're just now all over the moon, uncontrolled. And these things can survive the harsh conditions of space for decades. It is a real worry. In fact, it's something. So there's something called the NASA Office of Planetary Protection. So it's not fighting aliens. It's doing this contamination both ways, right? Us contaminating something else and something else contaminating us. And they say that our protocols are pretty inadequate based on what we know. So the strategy for Hayabusa is one of the reasons it's landing in Australia is because. Yes, one of the reasons it's landing in Woomera is because it's a pretty isolated place. The idea is once it lands, it will be taken sealed to the highest level that we can create in terms of contamination, which is good for these things that we know in that level of bacteria. It will be taken to a lab in Japan. It will be sterilized to the highest protocol levels that we have. It will then be moved to Canberra, to our lab, where we'll analyze it. So it is something that we have to be cognizant of. And this is actually part of a project. I have a project now that is trying to perfect the technique of mining asteroids, and one of these aspects is this contamination issue. Because it is a bigger worry now that we know what exists and what's been found on, saying, with Rosetta and stuff like that. So, yeah.
It's going to be slightly controversial, but is any of this technology actually going to help save life on Earth, as opposed to, sending us all to Mars?
So
they're spending a lot of money on it.
Uh-huh.
The planet is in a bad way, so, it's kind of...
So it depends on how you define save the Earth. Do you mean save the Earth or save humans?
Well, I mean, save all the animals that are on the Earth, because we're probably going to be able to save ourselves, but, mass extinction...
I don't think we can save ourselves. I don't have that much faith in us. No, so it's an interesting question. And so I think this goes back to, obviously, the money issue. So a good example is this. When Hubble was put up in orbit, the mirror that was installed was wrong, and they had to correct for it. The algorithm used to correct the distortion of the Hubble Space Telescope mirror is the same algorithm now used to detect tumors in medical imaging. Because again, it's the same sensitivity. This laser system is the exact one that we use for cleaning up space junk. And if there is a real worry that at some point space becomes so polluted that you will not be able to launch satellites. As soon as you lose your capability of satellites, most of modern day life is ended. And so one of the things that is happening is there's a lot better work going into the technology spin-offs of what we can do. One of the reasons I like mining asteroids is if you can get 100 years worth of lithium and nickel, well, most people have lithium and nickel on. Battery storage. One of the reasons we don't like it is because it is hard to dig up and there's very few pockets of it. However, if you get 100 years worth of it for essentially nothing, that means the price of battery storage is then essentially zero. That means then storing energy from any sector on a battery storage is the cheapest way possible. It's not negotiable. So there actually are a lot of ways now where what we're seeing in space is becoming quite important. However, all that said, I still think there's a fundamental thing here, and that is that space, astronomy, looking upward, not only do we get, when we give these hard challenges and hard questions to ourselves, we get hard solutions and hard results that we didn't know what to expect for. But at the same time, one of the things I think that is important for us to be humans is for us to be humans. It is to have that curiosity and wonder. And that this isn't a throwaway line. If we stop thinking about our place in the universe, then we just stop thinking, and then we stop existing, and then what is the point of survival? And this is what I think the great thing that astronomy and space unites is we can have these fundamental questions of, are we alone in the universe? How do we come to exist? Can there be something else that could seed life somewhere else? And so it's actually that intersection between both this technology that survives us, but also this fundamental quest that actually keeps us humans, that I think is quite important.
What can you dig into that? I appreciate your question, but my understanding of the human race is that we're actually not ready to colonise another planet because we can't work as a team at a global level to look after this one. And you say about the expenditure on space travel. We waste far more money on the planet fighting wars against each other, against other Earthlings, when we could be pooling those resources to do incredible things. But the human species doesn't evolve as quickly as, say, the jellyfish does. We still have Neanderthal characteristics, and that's why we can't live as an Earth species in a united way. So my approach to colonizing other planets, when we can look at this complexity, then we have the moral right to go and find the path to Mars. That's my approach.
I also just say I think we're in a race to say that, you know, the whole idea that we need to find another planet, Plan B, that doesn't work.
No.
Because it's not going to happen, because we're not going to get there. So we have to find other ways. Yeah. Sorry.
Yeah, I just wanted to go back to your balloons, the telescopes hanging
Yeah,
on the
yeah.
bottoms of the balloons, because I do astrophotography and I'm interested in that stuff.
Yeah.
What I'm interested is the telescope hanging on a balloon, you've got to stabilize it and that sort of equipment. Can you expand on that a little bit, some of the details?
Yeah, so being on a giant balloon doesn't necessarily make the most stable platform. The other trick is we've had to make the whole thing only weigh 20 kilograms, which is hard to have a half-meter telescope with the camera with the stability only weighing 20 kilograms. So we have three systems. You have a kind of a turntable that takes it one direction, right? So as the balloon drifts, the turntable counteracts it as well. We have a small gyroscope that works in azimuth direction that, again, as it kind of balances, it keeps it pointed. And then we have a third, which is a star tracker, which is essentially a navigator where it pinpoints a couple stars. Luckily, it's always dark, so there's always a few stars out there that we essentially lock onto. It's essentially a guider, and that does our fine pointing. So we can get 5 arc-second pointing. Yeah, it's one of the tricks is it's been hard to get to that stage. Why no one's ever done it? But yeah, we got there finally.
So what's the focal length of the scope and the camera size?
So it's very weird. So our field of view is 7.5 degrees. But because of the way the mirror system has to work, because we have what's called a Predator optic systems, we have a 5-mirror system. So that's why we have this huge baffle. So it's kind of, it's pretty sharp. We get distortions on the edge as well, but there's no way of doing it without more money and more weight. Yeah.
Sounds great.
Just about the Mars thing.
Yeah.
Judith, is it? She talked about people sacrificing themselves.
Yeah.
I've heard an NASA astronaut now, Walt Cunningham, talk about risk taking. He's done a few lectures on that, taking risk. It doesn't. You know, with the Mars One program, I met one of those guys in Hobart at Science in the Pub. It doesn't. Mars One didn't seem to have any shortage of volunteers. Didn't they have like hundreds of thousands of people?
Yeah, but there's no shortage of people who do a lot of stupid stuff as well, right? I mean, I wouldn't say that's a good argument, but I mean,
this guy's an engineer.
Yeah, I mean, I think it's probably Joe Richards. Yeah.
I don't know, maybe he was his comedy routine.
No, but I mean, the thing is this. I think there will always be people that take risks. I think there will always be risks associated with space. There's no way around it. But I think you have to realize this. I mean, I think it has to be. You take something like Mars One, which is kind of let the cap off all these risks. Where you have something like NASA that even says, "Oh, there's all these risks, and we're still going to take the risk, but it's still going to take 30 to 40 years to do that." You have to wonder what they're missing on the sun, right? I mean, just look at with all the reliving of the Apollo stuff. There was a lot of risk that they took, and there was a lot of stuff they didn't know that, and they still did it. So that same organization said, with this history, there's still a lot of stuff to do that will take 30 to 40 years. And then you hear the groups that say, I think this is actually where the conversations need to start happening beyond the room of astronomy and science. Kind of like what you pointed out at the end, right? We're able to do a lot of things now. We sometimes are not asking, should we? And this is this what society wants? And this is where space and astronomy is headed. That these things that were only sci-fi are now just things that we can do and think of with a little bit of money. But is that what we want? Is that what people want? Do you really want that the first, and I'm not saying yes or no, I'm just playing hypothetical, that the first humans who are the representatives of Earth to another planet are people who are very willing to know that they're only going to go there to survive for a little bit of time to die. Right? That's different than Apollo, where they knew there was a high risk, but they purely planned on coming back. Right? Or same as going to Antarctica. Or even other people going to Mars. And I think that's where the conversations need to happen.
But, I mean, today, you couldn't say to an employee, you're going to have all of these things that astronauts have,
Yeah.
and we're going to give you that job. You would, it's OH&S nightmare to be putting someone into that job, isn't it? So, it's going to be, you're going to go to Mars and you're going to die while you're there.
Yeah.
It is that crazy people are going to put their hand up, and they're not going to be American employees because they're all going to get over radiation for what they're allowed.
Something like that, yeah.
It's bizarre, isn't it?
It is. I think it's an interesting world.
Yeah.
It's good and bad in some ways. I think it's nice that it is accessible, that it's not just reserved for NASA employees, right? That space is becoming more and more accessible, but as it gets more and more accessible, we need to make sure that access is the access that we want.
And just on that, in terms of asteroid mining, who would have proprietary rights to those minerals? And which court would they be enforced in?
Yeah, okay, so...
Who was the last judge?
So let's go back to that legal issue we had. It is kind of the Wild West up there right now. The current treaties, which is governed by the UN, the Outer Space Treaty and the Treaty for the Moon and other celestial bodies in the late 60s, early 70s, says that anything in space is for all of humankind, which means anything brought back is for all of humankind. So no one would own it. The US in 2015 and Luxembourg in 2016 passed laws to circumvent this part of the treaty. There's 20 private companies set up to do this right now. There is no answer, and this is the issue. There's nothing to stop space piracy. There's nothing to stop that says, if you start a mining operation on an asteroid or the moon, and I go and take it, that's fine. So literally space piracy is something that people have to deal with right now. And so one of the problems that we're having is, how do we deal with this mess? Because we don't. So there's something called the UN Office for Outer Space Affairs, which kind of governs the laws of outer space. And there's now regular meetings from about 40 different countries, Australia is one of them, to try and update it, right? Treaties are not meant to be updated every year or two, but yet the laws and treaties that were written after the 67 is a very different world from what we're doing today. And so there's a push to make it towards a regulatory body that can kind of govern both the private and the public sector to make sure that what we're doing is kind of sensible. The model that I have for our mission is twofold. One, we want to move an asteroid and put it into what's called a Lagrange point. So these are points where Earth and Moon's gravity balances out. So we can move it and essentially just park the asteroid. The second part of the mission is either to take large parts of the asteroid and land it directly into Australia. It's actually not that hard, to be honest. It's actually the most economically viable as well. Or that you do remote mining in space and you bring it back down on rockets. We're aiming to have a prototype up in about 6 years.
Do you crash land?
But you don't have to be crash landed. We call it a hard versus soft landing. That's the industry term. We think we can medium land it in Australia. But one of the things is asteroids are giant chunks of metal. Most of the outside's iron. Iron is always going to be kind of worthless. So if you lose some iron on the process of re-entry, it's actually not a big deal. You want to get... Yeah. Sorry, last question. Yeah.
So you're talking about the delays actually getting straight from the Korean bullet and necessarily picking up soon. Is that actually known by the other countries who are everyone helping out with the effort, or is it being led by certain people?
So the only country in the world doing the laser stuff is Australia. So there are groups doing different aspects of space junk. We're the only ones doing the lasers for the small stuff. We can't build a big enough laser to take entire satellites down. The laser itself that we're building is 4 kilowatts, which is a lot. And that's to remove centimeter-sized objects. So bigger is the Death Star. But there are groups doing other bits. So the UK actually has built essentially a giant magnetic harpoon attached to the space station that goes out, releases a net, and actually grapples entire satellites and brings them back in. So space junk, though, is the issue that every country that doesn't like each other works together on. And that's kind of why you know it's an issue. But Australia is the only group in the world doing the laser stuff with the small bits, and other groups are doing different sizes. So yeah, it's kind of cool.
Thanks for coming in.
Yeah, no worries. Thanks for having me. Excellent.
Backpack day.
Thank you.
And doing a bumper sticker for.
Awesome. That's right. The rental car will know exactly what it's from.
Dessert or
I'll hang around for a little bit of dessert beforehand. Yeah.
That's good because there's lots of apple crumble, alright?
Yeah. So, yeah, that's right. And some people get double served, some people get none. Yeah.
We'll head back up to the
The laser on the telescope, is it the same size as the small spectrum?
That one's smaller. That one's smaller, actually. Yeah. So that's what I'm talking about. Yeah. Oh, did you? Yeah. Oh, okay. Yeah. No, the new laser system is literally about to come up next month. Yeah. So yeah. So there's 3 up there now. Yeah. So it's. You should. No, it's good. So EOS is entirely based at maximum all the options.
Oh, okay.
Yeah, exactly. So there's a group. Yeah, so there's a thing called the Space Environment Research Center, which is a collaboration between essentially